Hello, everybody. Welcome to the new session of neurodynamics. Uh, the lecturer is Professor Pipa, and I am Hamid, the tutor of neurodynamics course, Institute of Cognitive Science, Osnabrück University. So I can say that actually there's in Stud IP there is a section named Forum, and I made two categories over there. One of them, its name is subsessions, which I am uploading like sequentially the links that you need to watch the lectures by my YouTube channel or uh, other places and other persons so there are some lectures, for instance, that has been lectured and presented by Stephen Strogatz, which his book is the reference of our work. And also, well, you can also say about Izikevich. So in some, I can just tell you this, that in some topics, in general, I take those lectures, and because they are definitely they are teaching better than me. So in some cases, I take the main lecture, but sometimes well, we don't need a lot of parts of those lectures, so I should just do selective here. But some of them needs further explanation because you need to know some basic things. Therefore, I upload some other things as well, and this is really in need. Just at least look what is the content of the videos that I am uploading, and then or I am sharing, and it is already on YouTube. And then if you really know that what's going on and you don't need it, you can skip it. But if you have any problem or whatever, so I will be available to answer your questions. Therefore, the forum is for now it has two categories. One is subsessions, which you can find there the relative stuff, materials, and the other one is Brain Dynamics Toolbox, which for now it has just two areas. One of them is MATLAB installation, because I took a survey and nobody have installed MATLAB, and I know that you are okay with doing the project in Python or which language that you prefer. But about MATLAB, I'm not asking you to write your code in MATLAB. MATLAB, we just need the MATLAB software to be installed on your system to just do some very simple visualizing, like in a very visual way. You can just change the parameters and see the behavior of the system, and this is a need that we are working on Brain Dynamics Toolbox. Also, as Professor Pipa lectured, for instance, one of the topics in his lecture was Izikevich neuron model, or Izikevich. So there are also some MATLAB codes, so you don't need to do coding here, but you need to just have it on your on your operating system. So because the point was that because the operating systems are different, therefore I couldn't find something like uploading a video for MATLAB installation or something, but the German installation is uploaded and you can find it. And also, because you are students of Osnabrück University, therefore you access some images or installers of MATLAB, which you can easily find in the From that I have already installed. And then after, please sign into the Brain Toolbox, Brain Dynamic Toolbox website for simulating dynamical systems in neuroscience, and we will talk about it for this session. We will use one of those models. Okay, so here I can say that we talked about the MATLAB, installation of MATLAB, and also about the evaluation. Probably you got my email that final written documents will be the basic of evaluation process. So the practice sheets are just for learning, and feel free to ask your questions. Okay, so we want to talk about growth and decay, right? So if we say, for instance, that we have here in the right side we have x dot over x, and it's something like this or whatever, then let's take this one, like x dot is equal to x. Therefore we say that this is growing, or if we say like this, that x dot is equal to minus x, then it is decaying, right? In general, this is just a matter of sign in the function. So let's say what we are talking about here. We say we are talking about linear constant coefficient. So in this manner we say that there's a uniform motion, right? This uniform motion has a very simple structure, like dy over dt is equal to a constant named b. So this b is constant. And then we say that what is the solution? So this is separable differential equation. Therefore, you can find easily that this is the solution. What about growth or decay? Growth or decay, the simplest form, so this one, like a uniform motion, it was the simplest one. And this one, the growth or decay differential equation, is a very simple one, which it is saying that actually if you want to find the change in a function like y, it should be proportion to itself, right? So what is the suggestion for this? One of the famous one is exponential form, because if you take the derivative like d over dt of e to the power at, then it's going to be ae to the power at again. So you have the function itself again. So now when we want to talk about this form, we say that okay, this is linear, and there is some coefficients which are constant. Therefore we use a combination of them and we create this differential equation here. dy over dt is equal to ay plus b. This has a general solution, and its general solution is this form. y is equal to c e to the at minus b over a. And you can find the constants here based on your problem. So we are actually talking to reach a moment, because we are going to actually talk about 2D systems. And for these 2D systems, you already should know that actually if you want to, because we were talking about partial differential equation and chain rule and stuff. If you want to just take if this psi is a function of x and y, then you know about the terms, right? So I mean, in general, you know what partial differential equation in general is, right? If you have round over, I mean, the partial derivative of a function like y sine of x, if y is itself, if it is a function of x, therefore you should care about it. But if it is not, therefore you don't need to care about it, and you say y cosine of x, right? So let's go further and talk about autonomous equations, which has the general form like dx over dt is equal to f of x, and the general solution of it is this one, because there is no time in the function of f. And if you want to talk about equilibrium point, so I'm sure that you watched the lecture by Stephen Strogatz, but in general, this equilibrium or fixed point, or there are different types of names, but I mean, equilibrium can have the other meanings as well. But I mean, in general, you say that, for instance, if I have a function like sine of x, for instance, then you say that this is my fixed point, this is also my fixed point if it is x dot, and this is x. Why it is fixed point? Why? Because f of this point, I called it like x star, this is equal to 0, right? Therefore I call it fixed point, but I fulfill in it because it means that this is stable. And what does stable mean? It means that in the y-axis, which is x dot, it is increasing. For instance, here it is increasing the x, right? Therefore, it is going to be closer and closer to x. And if it is here, like a -1, like this here, this is a negative part, right? Therefore, it is going to take any state here. Well, this is a matter of any state here. It is going to, because it is that the x dot is minus, therefore kind of velocity will decrease and it will reach the stable fixed point. And if it is here, then it is going to go further. Therefore, there is no absorption here. Therefore, we call it like repulsive, and the other one we call it like attractive. And why we say this? In general, we say that actually. It is a matter of linearization, right? So if this is, for instance, Earth, and on this Earth you are living here, right? Or you can say that instead of it of being north or south, it can be south or north, right? And maybe you are living here, whatever. It doesn't matter. The thing that matters is that you build your house in a kind of thinking of a flat place. And this is linearization, actually. This is linearization. It means that near this place, you can say that actually this curve can be supposed as a kind of linear or flat place. Therefore, near equilibrium, you can say that actually this function here, near equilibrium, you can say that this works in general. So we talk about it in detail, but let's say that we want to now talk about oscillation. Okay, so oscillation, so we have a 2D system. Remember that we had a formula, we had an equation like this, for instance. Is it 2D or not? Yes, it is. Why? Because it is second order of differential equation, right? You have it, right? You have second order of differential equation. However, when you want to talk about it, we did it, right? When we want to reduce it to x dot 1 or x dot 2, then you will have two equations here, right? This is going to be two equations. So you here you had just one equation, but second order, and you transformed it to a two equation but first order. Therefore, you have actually kind of two variables like x1 and x2, and therefore you have kind of two-dimensional, not kind of, it is two-dimensional system. So let me actually clean here. Okay, so now we have now we want to talk about 2D systems. So we had a function, a differential equation like this. Dx over dt is equal to ax plus by. X is a variable, y is a variable. However, a, b, c, and d, they are constant. And if I want to find a solution for that, this solution is going to be x is equal to another parameter you can take, like v is, we talked about it, right? Because we have here like, let me not writing like this, maybe here this one is better, because we have x and this x is proportion to x again. Therefore, we are going to use e to the power lambda t. And same argument for y. You can also say that for the change in y, I am going to use another exponential term which brings the idea of first derivative of a function being generating the function itself. So in general, you can find a solution like this. Okay, you can test it. Actually, you can do this. So we call this like a simple ODE. Okay. the very simplest form that we will talk about it in this brain toolbox. So if actually so we were talking about the determinant and stuff, right? So if I want to say that, for instance, I am going to take, so you know what eigenvalue is now. You know what eigenvector is now, and so you have this matrix like A, B, C, D here, and you say that I am going to take to minus these two, like because we have 2D system and this is 2 cross 2. So I am going to take the determinant of this matrix equal to 0. If it is equal to 0, then I can find these eigenvalues actually. Therefore, you say A minus lambda times D minus lambda minus BC should be equal to 0, right? So I'm sure that you did it before. So if you do this calculus, then you see that actually this lambda, which is very important, it talks about a lot of parts of behaviors of the system. It is coming here, and you can say that, for instance, this v here, sorry, and this w here, they are basically they are a matrix. You can say that, for instance, I have a vector like v which has v1 and v2, and this is actually, you can say v and w. So this is just a naming, it's not important. By the way, for the matrix so if you do the calculus, you will find that this condition should satisfy, and the matrix notation like this that I talked to you is that I have a vector like x, and it is you can say that we have a kind of transform matrix like A times the vector itself x, and the vector x can be written as v as a vector, which I talked about it here, right? A vector v times a function that its derivative generates itself. So this the whole thing that we have written here, this formula, it is exactly same as this, right? They are same, but this is just in matrix notation. And the eigenvalue equation will be A times V is equal to lambda V as the vector. And by vector, I told you, right? I mean, by this, for instance, I mean a vector. So the if we say V is equal to 0, so we call V like a vector, eigenvector, right? Eigenvector, which definitely you know about it in the previous YouTubes that I shared, from 3 blue 1 brown, which is a very cool guy. So this non-zero solution is only exists when the determinant is equal to 0, which definitely you know. But this is just for recapping them. So we have different scenarios. One scenario is talking about growth and decay. So for our for our for our work, actually, we say that this lambda 1 and lambda 2, it can have different types, like it can be real or imaginary, which about imaginary part we will talk about it just a few minutes later. But if it is real number, like 1, 2, 1/2, pi, whatever, then if the second condition, which is lambda 1, is not equal to lambda 2, then you will have the growth or decay. So this is the sufficient condition for this. This takes place when this equation actually works well. Why? Because we had this, right? We had I have written already here, actually. So we have a, b, and x dot here, right? So if I want to at the end, if I want to solve this equation and stuff, it should be real. It means that under square there should not be a minus number, something like minus this is actually the imaginary number, right? I is equal to square root of -1. It can be, I don't know, it can be -2, for instance. It should not be any of them. It should be real. And the solution of lambda 1 and lambda 2 will correspond. These are the eigenvalues, right? The eigenvalues, they are corresponds to some eigenvectors which you are familiar with. So the matrix notation of it, which is not important, this green part, it's just for understanding. It's just a matter of notation, right? So we have two eigenvectors here, and we actually have two eigenvalues which are corresponding to this, and this is the general solution of it. This matrix notation of this differential equation is the general solution of this. So let's go further and see the relationship between lambda 1 and lambda 2, right? So if both of them are positive or negative, whatever, then both of them, we call it like node. And if lambda 1 and lambda 2, they have opposite signs, like one of them be positive and the other negative, then we call it saddle. Okay, it's just a naming. Okay, so now we want to solve for this example, finding the determinant and finding whether which scenario actually plays role in this. So for this I am going to, this is my matrix, right? And here and here I should I should say that actually this is, I am going to take this like minus substitute lambda, and then taking the determinant of it, right? So if I want to say something like this, then I would say 3 minus lambda, 2 minus lambda, 1 and 0, and then I am going to multiply these terms and substitute this term. Therefore the equation will be uh, 3 minus lambda times 2 minus lambda minus 1 times 0 is equal to 0, right? Because it was supposed to be 0. So therefore, what are the solutions here? The solutions here, one of them is this, that lambda is equal to 3. The other solution is lambda is equal to 2, right? We had this example in the video with by 3 blue 1 brown, and now we want to say whether it is a node or not, right? So if you say that both of them are positive, like here, lambda 1 and like lambda 1 and lambda 2, lambda 1 and lambda 2, both of them are positive. Therefore it is this situation, right? That both are positive, therefore we call it like node, right? Therefore we call this as a node. What node means? So we are going to now, soon we are seeing it in the brain dynamic tools, but you can just have it in your mind that in your phase space, actually a node, you have like in time series or whatever, you have something that is converging to, like you can say, for instance, I have a function like this and it is just going to converge to 0, okay? And so if you have a growth like this, it is just growing through infinity, right? I mean, so we will see this part in the brain dynamic tools. So let's go through the other one. So we want to talk about the, let me say, 0 minus wait, let me actually write it here. So 0 minus lambda over times 1 minus lambda, substitute the 1 times 1, right? What will it be? It will be lambda times lambda minus 1 plus or minus 1. Minus 1 is equal to 0, right? So we have this. And if you rewrite it, it's going to be lambda 2 minus lambda minus 1 is equal to 0, right? So if you want to talk about its roots, you say that I am going to square this. So it's going to be, this is minus 1, right? And this is your just this is your coefficient here, and this part. So you know about this, definitely you know. So you say that the way that I am going to find the roots are like lambda 1 and lambda 2 is equal to minus this one minus 1 plus and minus of square root of this minus 1 squared minus 4 times that, right? over 2 over 2. So it's going to be 1 plus and minus square root of 5 over 2, right? So it is very, because square root of 5, how much is the square root of 5? Square root of 5 is equal to, it is bigger than square root of 4, right? Therefore it is bigger than 2, right? Therefore 1 minus 2 will be minus, and 1 plus 2 or something bigger than 2 is plus. Therefore you have two solutions. Lambda 1 is bigger than 0 and lambda 2 is smaller than 0. One of them is positive, the other one is negative. Therefore you call this one, so this is this situation, right? This is this situation. Lambda 1 and lambda 2 are, they don't have, they have different opposite signs. Therefore we call it like saddle, right? Okay, so this was two examples for nodes and node and saddle, which is coming from the idea of that actually lambda 1 and 2 are real, there is no imaginary part in it, and lambda 1 is different, I mean the eigenvalues, they are not same, therefore you will have growth or decay. So now I just suppose that you already installed MATLAB. So if you install MATLAB, you can actually see that like something like this will be open, right? So I am going to, so this is the name of this part is like command window. So in command window, whatever it is, so I say that I say where am I? So this is going to give you the address, right? The path that you actually are. So if I just run the MATLAB like normally, I'm going, my path will be at home. So I know that, for instance, these models of the toolkit named Brain Dynamic Tools are saved here. So I know this address, whatever it is, it doesn't matter where you are, whatever it is, in command window you write add path, and what did they do? I didn't copy this probably. Maybe I think yeah, it doesn't work in, it just work in terminal, but let me, but this is in MATLAB. Let me try again. Yeah, it works. Yeah, but in terminal it doesn't work. Actually, copying by keyboard, I don't know. You need to uh, set something. By the way, so you have this add path, and actually before this you need to add this part of the address. I mean just this, and then the model itself, and that's the only thing that you should do, like add path, the BD toolkit, as well as its model. Okay, so now we want to look what kinds of models it has, right? So you can, for instance, write ls, and it's going to list all of them. And actually, you can also find it here as well, right, in the left panel. By the way, so these are the models that you can actually achieve by this fantastic brain dynamic toolbox, which is designed by Stuart Heitman from Australia, and you can be in direct contact with him and ask your questions as well. So we talked about ODE, and this in this ODE, ordinary differential equation, we can look, for instance, for the model. There is this model named, if I can find it actually here, uh, linear ODE. I should search for, yeah, here. This is this model. So we are going to run this model. So we write like help linear ODE, and I use the tab, and it's going to tell me actually the author is Stuart Heitman, uh, a very friendly and nice guy which you can follow. And I suppose that actually you did and you registered in the workshop. So it is going to tell me that actually when inside these parentheses there is nothing, it means that it doesn't take like because some models they have a kind of parameter or variable here, and you need to set that in the beginning, but this one, it doesn't have anything. So you can just say, okay, I'm going to just copy this. This is an example, right? You can run these examples. So I am going to take this as the system which is designed, probably you participate in the workshop. So this GUI, which is a command like BD it is going to create this visual kind of representation of this system, which is here, it is linear ODE. So it's very simple. Whatever the model is, you just write the system is equal to what was the name of it, linear ODE parentheses, and I do the semicolon to not showing anything, but you can also write without it, and it is going to tell you information about the structure of the system that you created. And you can find these, for instance, this is the time between in this interval, and you can, and these are the solvers, like this one for instance is ODE Euler, which we will cover, and we will talk about it in one of our practice sheets as well. But you can have other types of solvers of differential equation solvers, like Ron-Kutta, second order, fourth order. Yeah. By the way, so you say that GUI is equal to GUI of your system, and it's going to create this for you, right? So now you have this, and we all learned that we can use the larger equation. So this linear ODE is a system of linear ordinary differential equations, which x dot, which we were talking about, is equal to ax, which is a function of t, plus by, which is again a function of t, as well as y dot. It means that the changes of y with respect to time is equal to c, which is another constant, times x. Therefore, the differences, the way that actually y will change with respect to time, it depends on the value of x, as well as the value of y itself, and we were talking about it, but now we want to see that actually what it means. So here you have the parameters. You have in the right side you have a, b, c, and d. So we had four examples, right? For those four examples, so one of them was, for instance, the one that gave us the node, and uh, the the values were like 3102, 310 and 2. Okay, so let me check actually whether it is in it is not inside the, but you can do this, and you can also do this. I don't think it actually matters, but by the way, we do it. So this is just the range of the numbers that you can choose. By the way, so we tick it again, and we have these values, right? 3, 1, 0, and 2. And based on our example, we were supposed to see a node. Okay, so now it is wrong. How can we get that here actually in this part you can see that the progress is 100% and it is finished, and this is the number of steps, and this is the CPU time, and you can just do other types of you can use other types of solutions or the algorithms actually that you can solve the differential equations. Therefore, so we want to see the time portrait. So the time portrait is something like this. It is a portrait of X with respect to time, as well as a portrait right like Y with respect to time. And you can see that here you can choose the variables. We just have two variables and we have two panels. So we, as you probably learned in the workshop, we can calibrate the axis. And you see that this is actually a kind of growth, and it is just going to a point. So you see that this is the way that it is going to evolve with respect to time, both X and Y. Okay, so we call it node. And the face portrait is something like this. The face portrait is here you can imagine of a variable like Y with respect to a variable like X, and be careful about this, that it is like with the order of 10, 10 to the power 24 or 10 to the power 16, and these are the big numbers. So if you just again do this evolution, you will see that actually exactly at that time, that's the in the time portrait that suddenly changed happened. You can see that here in very fastly it is going to reach that point. So if I change the domain of time again, for instance, about instead of 20 I write 30, then you will see that actually uh, again I will have this situation, and again at very close to 20 you see that it is here, and then so maybe collaborate the axis. So you see that again it's a kind of respectful thing, relative thing. So okay, let's see what saddle is like, how saddle looks like. For saddle we had, for instance, A was 0, B was 1, and C and D was 1. We're 1, so we see that in the time portrait, we see that this is one of the stupidity actually of Apple MacBook and all of these Apple devices. And by the way, so if we calibrate our axis, you will see again that x, and with respect to time, it is going to be to absorb to this, and about the phase portrait also it is same. And but the point about this saddle is that from it is from one side it is like uh, absorbing, and from the other side it is repulsing. Okay, now we want to talk about imagination. Some people are saying that one of the things that makes science dull and difficult is that it takes a lot of imagination. It's too hard to imagine all the crazy stuff that things are really like. This is a sentence by Feynman, actually, which remind us that actually this imaginary part is very important. So we want to go through oscillation. Oscillation, you know about this oscillation, right? This simple harmonic oscillator, for instance, we talked about, or you have other kinds of oscillations as well. Some people are saying that oscillation means that there is a kind of frequency, which we show it by f, and these are because of its relationship with time and stuff. They claim that they can be even the building blocks of the whole universe. This is Therefore this is a very important concept. You can use it in a lot of senses, in a lot of fields of studies. So we want to talk about imaginary number. So I'm sure that you have this idea that uh, we have something, sorry, named complex numbers. And for the complex numbers, we say that we have something like I. We have something like I, which is equal to square root of minus 1. Okay? So we have this. And the way that they explain it is that we say we have real numbers over here, and we have imaginary number. What does it mean? It means that in this sense, if you want to change from real number to imaginary number, it means that actually if you have a point over this, then it's going to rotate here like 90 degree to another point like I. Okay, so I is the basic element of our imaginary axis. Okay, so if you do again like this again another 90 degree, you will face something I2, right, which I2 is actually equal to square root of minus 1 squared. Therefore it is going to be, let me actually write it here. So if I have I2, then this I2 will be equal to minus 1, right? So it means that if I do this 2 times 1, if I do this 2 times, it means that I am going to rotate it 2 times, uh, which means actually I am taking something from positive to negative, right? What did I do? Okay, so I am taking something from positive to negative. This means that actually the imaginary number is basically it is a talk about rotation. Okay, so uh, so you know about it enough for now, I think. So let's go and talk about Euler formula. Euler formula. So and just let me say that actually here in general we say, for instance, if a complex number, it is equal to a real part, like say it like r, plus I times an imaginary number. You can say it like a is equal to ib or whatever. So I mean you can say that it is consisted of some real parts with combination of this imaginary part. Okay, with combination of imaginary part. And if I have something named conjugate of it, like SC star, A, which is the real part, will remain, and the imaginary part are going to be in the minus form. And after that, if you do CC star, you can actually measure the amount of the size of complex number C. And so these are not important, but just for for making your mind ready. So this Euler formula is this one, which is a very important formula. It is very important. So Euler formula is actually saying that if here in Ri axis diagram, if I have a point like this, then this is going, the one that is on the r axis, the real part, is going to be cosine of theta, right? If this angle is theta, then this is going to be cosine of theta. And also you can say that this part, I mean until here, it is going to be sine of theta, which it is in the axis of imaginary part. Therefore, we are going to say that this is actually going to multiply it by I. Okay. So actually we say that if I have a point, for instance, here, if I have a point like this, take this, and if I bring it to this part, then it means that this theta is proportion, like in an exponential expansion. You can say that the real part is cosine of theta and the imaginary part are sine of theta. So we should remember this Euler formula, or if you can actually prove it. It's not that much hard. And but I mean, you don't need to remember it. I mean, just for this lecture, even during exam, you can access this. You don't need to memorize these things. By the way, So now we want to talk about oscillations, right? For oscillations, we need actually imaginary numbers to emerge in our differential equation. I mean that when it is not imaginary, it is so much boring. It is just a node or saddle one. There is no oscillation. For having oscillation, you need complex numbers. You need complex numbers. Therefore you say that for this oscillation, first it should be complex. What should be complex? Eigenvalues. We were talking about eigenvalues. And in our first scenario, the eigenvalues was real. They were real. But here it is it is complex and unequal. Therefore, we will have, and they are complex conjugates that we talked about, like, well, I showed it like C star over here, but here you can say, I don't know, tilde or hat or whatever. I think hat. By the way, it's not that much important. The important part is that if it means that basically, uh, it means that, so it is not, it is, I mean, with W, if your lambda is equal to alpha plus I omega, and alpha is a plus d over 2, a plus d over 2 here, and as well as, uh, your omega is a positive one, is bigger than 0. All of them actually is saying that if this condition over here, uh, if it is not falsified, if it stays valid, if it is not violated, then your you will have this oscillation because of the basic structure of math. So I don't want to go into it that much, but you can just say that in matrix notation, you will have like vector of u plus minus vector of v times I, and all of them are eigenvectors. And you know that actually eigenvalues are corresponding to eigenvectors. So in general, you can find the general answer for x, which is, this is an important thing, right? Because it is coming from Euler formula. Which actually you can say that this exponential, this part is the real part, and this part is coming from those imaginary parts, which one of them is cosine, the other one is sine of theta. And this c over here means that how much is the amplitude of 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 your oscillation actually is. And this theta is talking about the kind of change and difference and phase of your oscillation. By the way, this is just a matrix notation for that. It's not, you don't need to remember or memorize it, but we want to go deeper and more visualize in it. Therefore we say, we have two types of lambda, two types of oscillations. One of them is center, the other one is center, the other one is spiral. So if lambda and lambda hat, if they are pure imaginary, it means that alpha is equal to 0. It means that actually in our formula, because we had this, right? We had this ax plus by and cx plus dy. One of them is equal to x dot, the other one is equal to y dot. We had that actually this a, if this a is equal to minus d, it means that here this a is equal to minus d, then you will have a center. But if this a, it is not equal to d, then you will have a spiral. Why? Because your real part is not 0, and this non-zero real part gives you, in lambda and lambda hat, it gives you spiral form of oscillations, which we are going to talk about it in Brain Dynamic Toolbox and see that how can we actually visualize these things. But before that, we need to have some examples, right? Because in computer you need to give some numbers, and let's say we have an example. So I am going to say that, for instance, if my a is 2, okay, I want to make something center. What should I do? I should say that d is equal to minus 2, right? And now I can say that, okay, b is minus 1 and c is 10. With this, then I am going to say that my matrix actually will be 2 minus 1, 10, and minus 2, and I am going to say that I take this lambda here, and then I say I am going to do this, right? This minus this, or maybe not, maybe like this. No, doesn't work. By the way, you know that. So you say that 2 minus lambda times minus 2 minus lambda minus 1 times 10. This should be equal to 0, right? So what is lambda 1 and lambda 2, or lambda and lambda hat, So lambda or lambda I don't know, hat or line or whatever, it is going to be this, right? It is going to be, so we have, basically here we have this, we have this 2 minus lambda. It is going, let me write it actually. It's better. So I have this 2 times 2 right here. 2 times 2. So it is going to be minus 4. And 2 times minus lambda, it is going to be minus 2 lambda. It is going to be plus 2 lambda. It is going to be plus lambda 2 plus 10, right? Therefore this and this is the beauty of that thing actually, that choice. So it is going to be lambda 2 plus 6, which is equal to 0. Therefore what is lambda here? Lambda will be I mean lambda 2 will be minus 6, right? Will be minus 6, right? Therefore your lambda will be minus square root of 6. Sorry, square root of minus 6, right? So this is your lambda, and your lambda hat is equal to so one of them is positive, the other one is negative, right? So both of them, I mean lambda 2 is equal to lambda hat, right? So because of this, then you have this imaginary part, which is imaginary, right? What is this? You can say that this is going to be like 6i, and this one is going to be, I mean square root of 6i, or you can write I over here, and this one you can write minus I square root or whatever. Therefore it is because of this choice, right? Because of this A2 and D, and we had this here, therefore we have pure imaginary root, therefore we have center with this choice. With this choice here, over here, with this choice, we have center. So let's go and solve another example. We want to find something that is spiral, right? We want to find spiral. For a spiral, we should say that I have A and I have D, and they should not be like A should not be equal to minus D, right? Therefore I take these, and for the sake of having imaginary part, because this condition just tells you that this is not going to be pure imaginary. It will have some real parts. But if you have because you want to have other types of you want to have in general imaginary part as well, therefore this situation will give you so I am going to take the determinant of 1 minus 1 10 and 2 minus 2, and this is going to be 0. Therefore I am going to write here, right? I am going to add it here on the diagonal of it, right? So therefore it is going to be 1 minus lambda times minus 2 minus lambda minus 1 times 10, right? So this is going to be minus so actually this part is like minus lambda plus 2, right? So if I put the minus over here on this one, then I will have like lambda minus 1 times lambda plus 2 plus 10, which is equal to 0. Am I right? Am I right? Therefore, well, it's not important. I don't know actually why I was. So in general, if you do this, it's you will take lambda 2 minus lambda plus 2 lambda minus 2 plus 10 is equal to 0, right? It means that lambda 2 plus lambda plus 8 is equal to 0. So what are the lambdas? The lambdas, uh, they should be this, right? They should be minus this one. So we have a 1 here, right? We have a 1 here. So minus 1 plus and minus square root of that 1 to the power 2. So maybe 1 to the power 2 minus 4 times, we also have another 1 here, right? Therefore 4 times 1 times 8 over 2 times this one. So in general you will have an imaginary part. And why is that? Because this 4 times 8, this part is a huge one, and it is bigger than 1 squared. Therefore it will have imaginary part. And what about this one? This one is the real part of it. So it is not 0, because we chose that actually A is not equal to opposite of D. Therefore we still have real parts. Okay, so what now? So by spiral we mean that actually we are going to see some pictures like these beautiful pictures. So now we have the spiral example and also center example. So with these choices, and then we can talk about it based on I just figured out that I said something wrong here. This here in this I said everything that I said was right, but here actually I don't mean this dot, right? We are not taking this dot to here. We take this is the rotation of this dot, right? This point. So we take this here, and then we say that the real uh, part is going to times this cosine of theta, and the imaginary part are going to times the sine of theta. So that was all. So now we can talk about these center and spiral in brain dynamic toolbox, the model, which is ordinary differential equation, which we are familiar with. Let's investigate it a bit more. Okay, I want to talk about two other things as well. Uh, so we were talking about node and saddle, when actually we don't have any complex number in our solution, right? So here we say we instead of these values for our parameter, we use for spiral form. As we see that a can be 1, b minus 1, and c 10, and d minus 2, right? Why? Uh, so we saw it actually in our example, right? So if I see actually how it is, I see that actually it in time portrait, which x is with respect to time, or y with respect to time, it depends on the initial condition, and you can choose initial condition over here as well, or you can change the initial conditions. In general, it's not that much important. So if you see that actually with time evolution, it is going to converge to something, right? When the time is increasing, it is first like kind of uh, fluc- not fluctuation, actually kind of big perturbation. You will see a big difference, and then after all it is going to converge to an optimal value with as time goes through infinity. By infinity we mean physical infinity, right? So the phase portrait will be something like this, right? It will be an spiral which can start very fast from that initial point, and it can just goes and goes and goes and absorb to a very single value. Okay, so this was the spiral. Now we want to look at the other type of solution, which actually it has the imaginary part, but the point is that A is exactly opposite of D, right? So if we do this, then we will see that actually in the time portrait, you will see that x with respect to t, it will have a very informative shape, very predictable as well as periodic, and you will see oscillation basically. And by oscillation, you see that it is very similar, for instance, to sine or cosine functions. And you see that by the evolution of time, it is just repeating. And when you look at the phase portrait of it, in the phase portrait, interestingly, those shapes are going to be kind of circle, right? Something like this. That this is the starting point, and this is the ending point. But it is just going through this trajectory. The name of it is trajectory technically, and you will see that actually this is just repeating and repeating and repeating. Therefore, it is actually one of the dynamical systems perspective of how in which situation you can see oscillations. Oscillations has a meaning, and we are very much interested in oscillatory systems because we look at neurons as oscillatory, as oscillations when they are spiking, right? So this was the phase portrait, which actually uh, is an interesting thing. So we got a lot of ideas about ordinary differential equations in, you can say, about 2D systems, which you can actually have uh, two dimensions. And we also know that now we know that what Jacobian, what Taylor series, what Jacobian is, how can you take the determinant of a two times two matrix, how you can actually find whether this ordinary differential equation has imaginary solution or not, and if it has the solution which is an imaginary solution, then if it has imaginary solution, then you will see two type of things, whether it is a spiral uh, or center, right? So the only way of not having a very boring, a very boring equation, like ODE equation, is that we'd rather have imaginary solutions. By the way, complex numbers playing magic. So until next time, if you have any question, just let me know. Hope you enjoyed.